Imagine driving at 60 miles per hour, but then hitting dead-stop traffic for the majority of your journey. If we simply average 60 and 0 to get 30, we ignore the fact that we spent far more time sitting still than moving. The resulting number doesn't reflect the actual rate of the trip. To find the true rate of travel, we use the core definition. Average speed is the total distance traveled divided by the total time taken. Because distance measures the ground covered regardless of direction, average speed is a scalar quantity. It is always positive for a moving body. Average velocity, instead, measures the total displacement over the total time. Since displacement tracks the straight line change in position from start to finish, it includes a specific direction. This makes average velocity a vector quantity, which can be positive, negative, or zero. When solving for multi-stage journeys or varying speeds, the most reliable approach is to return to these two foundational fractions. Total divided by total. We see how that foundation expands for specific time intervals. If an object travels at speed v1 for duration t1 and then shifts to v2 for duration t2, we calculate total distance by adding the product of each segment before dividing by total time. When split by distance instead of time, we rewrite the denominator. Time is found by dividing each distance, d1 and d2, by their speeds. If distances are equal, this simplifies to 2v1 times v2 divided by v1 plus v2. The mathematical relationship is determined by what remains constant. A simple arithmetic mean only works if the time spent at each speed is perfectly equal. If the distances are equal, the harmonic mean we see here is the only accurate calculation. Distance accumulates continuously, but displacement can decrease if an object changes direction. Therefore, total distance is always greater than or equal to the magnitude of displacement, meaning average speed will always be greater than or equal to the magnitude of average velocity. A 2.5-kilometer forward journey at 5 kilometers per hour takes 30 minutes. The return lasts 10 minutes at 7.5 kilometers per hour. Converting 10 minutes to 1/6 of an hour ensures consistent units, giving a 1.25-kilometer distance to calculate final average speed. Solving these problems requires tracking the distance and time for every individual segment, while strictly maintaining unit conversions throughout the process. A journey splits into equal distances, x. First segment speed is 3, so time t1 equals x over 3. The second segment has two equal time intervals, t2, at speeds 4.5 and 7.5, giving the equation 4.5 t2 plus 7.5 t2 equals x. Try to solve for t2 in terms of x on your own. Once you have that, set up the complete average speed fraction for the entire journey before we move to the solution. To isolate t2, we combine the terms in our second equation to get 12t2 equals x. This means t2 is equal to x divided by 12. Now we construct the total distance over total time fraction for the path. The distance is x plus x, and total time is our t1 value plus the two t2 intervals. Since variable x appears in every term, it factors and cancels out completely. Once the variables are removed, we are left with a purely numerical calculation. Evaluating the remaining fractions results in a final average speed of 4 meters per second. Mastering these problems requires drawing clear diagrams and adhering to total over total definitions. If the setup is correct, the variables resolve themselves.